Thank you, John. I'm really honored to be here this evening. I started at Microsoft because I really wanted to see how mathematics and computer science and also physics could come together to make a difference in our world and really have big impact. I actually learned about quantum computing in the late 90s from Andrew Wiles. He taught a course on cryptography when I was at Princeton. And I learned from him that there was a computer, a model of computation, where in fact you could break problems that we thought not possible to solve on digital computers. Namely, that you could break RSA encryption with a quantum computer. I became fascinated by this and decided to pursue quantum computing. And now I like to joke that I write software for a computer that doesn't yet exist. But at Microsoft, I now work for another Fields medalist, Michael Friedman, who founded Station Q, part of Microsoft Research, a lab dedicated to studying quantum computing and the really magical properties of this model of computation. So I'd like to share with you what we might be able to do with a quantum computer. To whet your appetite, this is what a quantum computer looks like today. So on the left, we have a picture of Charlie Marcus's lab at the University of Copenhagen. And you see these large doors hanging from the ceiling. Those are dilution refrigerators. And inside, when you remove the shield from one of these refrigerators, you would see what is shown on the right. These are layers of temperature and copper to actually cool within this refrigerator down to millikelvin temperatures at the very, very bottom, going from room temperature to millikelvin. And in that millikelvin environment sits this wonderful quantum chip. Coldest place in the universe is right there. So what can we do with such a device? Well, there's quite a few areas we can actually look at where we already know that quantum computers will be quite transformational. Quantum computers promise to be as transformational, if not more so, than digital computers over the last 60 years. Areas where quantum computers promise new solutions and better solutions include privacy and security, for example, breaking RSA encryption, as I just mentioned. In the energy space, we can think about developing a room temperature superconductor where we might be able to then develop maglev trains, lossless power transmission, even smart grids. In the space of the environment, we would love to combat global warming. And there we can hope that with a quantum computer, we can begin to design a catalyst that will enable efficient carbon capture at any point source, not just fixed point sources like fossil fuel plants. In the space of machine learning, quantum computers promise better solutions and learning better models of data and of users. And in the cloud, we can just imagine a quantum computer sitting in the cloud where you can actually turn to the quantum computer for solutions that you could never ask of digital computers, that you couldn't ask of supercomputers. It's quite amazing what that might be able to do for business, for communication, for the problems we're all looking to solve today that we can't on digital computers. So what are some of these problems that we can't solve and we can't hope to solve on digital classical computing technologies that we have today? Well, here's one problem that I've already actually mentioned. Here's a number. It's a somewhat large number. It happens to be 2048 bits. And this problem is to identify the two numbers, in fact, the two prime numbers that I multiplied together to obtain this large number. This problem is known as factoring. Find these two factors. Can anyone solve this problem? Well, if you could, you would deserve a very large prize. In fact, on a classical computer, what we know about this problem, this problem called factoring, is that For the 2048-bit number, this will take 1 billion years to solve on the fastest computers we have today, or even the fastest computers we can imagine decades from now. On a quantum computer, however, the amazing insight that Peter Shor had in 1994 when he first published this algorithm was that a quantum computer could actually speed up finding the solution to this problem. And if you look at realistic clock rates for a quantum computer, we could solve this in 100 seconds. Now, factoring is the problem that sits below RSA encryption. This is the mainstay of e-commerce today. Every time you put your credit card on the internet, it's encrypted using RSA. Now, with a quantum computer, I'll have a lot of shopping to do. Let's look at the fundamental scaling difference between a quantum computer solving this problem and a classical computer solving this problem. So if you look on the x-axis, we have the number of bits in the number that we want to factor. In the example we've just looked at, that was 2048 bits. On the y-axis, we have the time that it takes to factor that number. Now, the time it takes on a classical computer scales like these blue lines. The lighter blue line is the time it takes on a classical computer we had around 2003. With a faster classical computer, a bigger supercomputer, say from the year 2018, we expect almost the exact same scaling. In fact, it's the same scaling. We haven't really improved things much. It still scales super polynomially. With a quantum computer, we can look at two different clock rates, and you can see that this is a fundamentally different scaling than the classical solution, than the classical algorithm. And here we have two different clock speeds, a megahertz and a gigahertz quantum computer, and you can see that both they scale linearly. This is exactly what we want to look for when we're identifying possible applications, possible quantum algorithms. So here, again, for a 2048-bit number, we see that on a classical computer, it's 1 billion years. On a quantum computer, 100 seconds. Now, you may think, just move to a larger key size. Increase the number of bits in your number to factor. But you can see that as we move to 10,000 bits, this still is efficiently solvable on a quantum computer. Maybe now it takes me a day. That's still pretty amazing in comparison to the 1 billion years on a classical computer. So you may ask, does this type of scaling difference between classical and quantum algorithms, does this exist for other types of problems? This is one type of problem in cryptography, but perhaps there's others. And indeed there are. We can think about Feynman's original ideas that John just spoke about. Feynman's ideas of using quantum mechanical systems, of using a computer built from quantum mechanics to simulate physical systems, a natural marriage, if you will. And we actually look at simulating physical systems already today on supercomputers. If we look at the amount of time we spend on a supercomputer, how much time we devote to actually simulating physical systems, well, remarkably, it's almost 50% of supercomputing time today. And that's the time spent on problems we know how to solve on the supercomputer. Just imagine how many problems there are out there that we would love to solve on our supercomputers, but we can't. Problems that we may be able to solve on a quantum computer. Here's an example of such a problem that we could solve on a quantum computer, but we cannot solve on a supercomputer today. We'd like to understand the electronic structure of, say, a molecule. Here, for example, ferredoxin is a molecule. This molecule happens to be used in many metabolic reactions, including energy transport and photosynthesis. We'd like to understand the ground state of this molecule. So the goal is to find the ground state. And on a classical computer, this is intractable. It's really longer than the lifetime of the universe to solve, to actually find this ground state. So it's not efficient, and we can't hope to solve it on our supercomputers. However, on a quantum computer, we can hope to find the solution. And what we know about this problem is that on a quantum computer, we have efficient solutions. Now, efficient, as a computer scientist, means it can be solved in polynomial time. So in 2012, we all would have said, well, that's efficient. This problem is efficient on a quantum computer. However, when you plug in the clock rates to our efficient quantum algorithm, which is faster than the classical algorithm, it was 24 billion years. That's not quite efficient enough for a practical application. So what we did, my colleagues worked on actually identifying how to optimize this quantum algorithm. Can they make it even more efficient with circuit optimizations, software optimizations, and better mathematical bounds, proving better properties about this algorithm? So through a combination of mathematics and software, over 3 years, they were able to get this runtime down to an hour. This is now really a possible, potential killer application of quantum computers. The space of simulation of physical systems, of finding the ground state of molecules, such as ferredoxin. So you may wonder, why do I care about finding the ground state of ferredoxin? Does this algorithm have other applications outside of just this problem? Well, naturally, it does. So possible other initial applications of a quantum computer include looking at problems like nitrogen fixation. Here, we would love to be able to identify a catalyst that allows us to more efficiently convert nitrogen to ammonia. Right now, we actually use a process called the Haber process to produce artificial fertilizer. The Haber process was developed over 100 years ago. With all of the developments of technology, we still use a process to develop artificial fertilizer that was developed over 100 years ago. It uses 400 degrees Celsius temperatures, 200 atmospheres of pressure, and lots of the world's natural gas. If we had a catalyst to actually improve this reaction, to perform it more efficiently, this could really transform the production of artificial fertilizer, the cost of producing such fertilizer, and potentially make an impact on producing food more efficiently around the world. We can study such catalysts and hope to identify such catalysts with a very small quantum computer of 100 to 200 computational qubits. Another example of a catalyst that we'd like to study on a quantum computer is in the space of carbon capture. So again, we would like to combat global warming. We need to extract waste carbon from our environment to do so. And we have not yet identified an efficient way to extract waste carbon when it's in a mobile point source, from a mobile point source, such as an airplane or an automobile. Right now, we extract waste carbon primarily from fossil fuel plants at the location. A quantum computer may be able to actually help us identify a catalyst that could help us more efficiently extract carbon from the environment. Another area is in materials science. A quantum algorithm can help us study and understand materials that may actually superconduct at room temperature. And here, this could enable smart grids, lossless power transmission, and eventually also maglev trains. Now here you can think even of the snowstorm we're seeing on the East Coast right now. Imagine being able to take solar power harnessed, say, in Phoenix, Arizona, and transport it losslessly to the East Coast where they may have 2 weeks without power. This could make a big difference in our energy usage. And finally, in machine learning. Machine learning is pervasive across all of technology today. And with a quantum computer, we may actually be able to more quickly train models of users and data, and we may also find better models. We can actually begin to ask different questions we can't ask of a digital computer. This could be quite exciting for how we understand ambient intelligence to be today. And again, this is with a small quantum computer. Now, with all of these applications, we also need to think about how we're going to program the quantum computer. And coming from a company founded on software, of course, we want to understand how software might also allow us to more rapidly innovate towards achieving a scalable quantum computer. We've been developing a software platform, or we like to call it an innovation platform, to allow you to program a quantum computer, to actually input a quantum algorithm, translate it to a quantum circuit, and then eventually optimize that quantum circuit and send it to the actual piece of hardware that we saw in the early slide. We can also send it to a simulator, which we've done today. And the example where I mentioned going in quantum chemistry from 24 billion years down to the algorithm we have today, we actually understood a lot of those optimizations through this software platform. As we know, from the time from transistor to, say, chip was quite a long time. And had we had the software to enable more rapid innovation, we may have seen that time shrink. So we hope by developing software in advance of having the hardware fully scaled, we'll be able to actually move the needle more quickly. This software is, in fact, available on GitHub. So I really thank Feynman for laying the foundations of quantum computing. And his foresight occurred at a time when digital computing was in its infancy. In fact, you can trace these ideas back to as early as 1959, his ideas of quantum computing. It's absolutely amazing and exciting that today we're actually seeing these ideas come to life. Quantum computing really promises to utterly overturn our notions of computing, what it means to compute, and how we compute. I'm really excited to see how it will take us quantum leaps beyond how we compute today. Thank you.